today's lecture is going to be a review session. We will go through the last semester's midterm, or one of them, or midterm for section 3. Okay, so I'm gonna start with question 2. So question 2 is worth 35 points, and it's on assignment number 1. So it tests your understanding of assignment number 1. And as I always emphasize, assignment number 1 is not a coding exercise. It's an assignment that is intended to teach you the concepts of parallel programming and shared memory communication. So if you can answer these questions, then this means that you have understood these concepts. Which line? So I'm giving you the producer-consumer code, or a possible way of writing the producer-consumer code, because it can be written different ways. Which line in the above code does each of the following? Waiting if the buffer is empty. So who waits if the buffer is empty? Producer or consumer? Yeah, consumer waits if the buffer is empty. And where is that waiting done?
6.
Yeah, line 6 in the consumer, which is the while loop. Okay. Now, next question. Updating the value of n in the shared memory buffer. Who updates n in the shared memory buffer? Producer, and it's this set n. So these are straightforward questions. Now the question that requires more thinking: what will happen if we delete set in on line 6? So in that case, what will happen? Will it work correctly? How many items will get produced? How many items will get consumed? And what's the explanation? Okay, so if we forget this, if we delete this set in, what will happen? How many items? Produced items? Consumed items? What will happen?
Produce m minus 1.
What's that?
Produce m minus 1 item.
Produced, you are saying m minus 1,
Yeah.
and consumed
0.
0. Why?
Why? Because.
Because.
Yeah.
So what does set in do? Set in puts the value of n in the shared memory buffer. So the way to think about this is that these in and out, you have 3 copies of each one of them. In the producer, you have an in and an out. And in the consumer, you have in and out. And in the shared memory buffer, you have in and out. And initially, all of them are 0. Now, normally, the n on the producer side is going to go from 0, 1 through m minus 1. Because the question is, by the way, m is the buffer size. M is buffer size. N is item count. Make sure that you use the variable names that are specified in the question. M is the buffer size, N is item count. Okay, so this is going to go from 0 to m minus 1. And on the producer side, again, m is going to go from 0 to m minus 1. But now in this case, the problem is here. The problem is here. If we don't set in does this. Updates this with this. But if we don't do it, n will stay 0. So if n stays 0, what will the consumer think? Yeah, the consumer will think that nothing has been produced. So the consumer is going to consume 0. Now, what will the producer think? Well, the producer will stop when the buffer is full. Now, will it think that the buffer is full here? Well, in fact, no, because it's doing get in. So it's checking this condition based on the in that is coming from the shared memory, which is always 0. So it will think that the buffer is never full. And the producer is going to produce n items, not m minus 1. Now, this will become m minus 1 if we change what? What change will make the answer here m minus 1? So the m minus 1 was based on the assumption that the producer knows that in is getting updated. So if we change this get in, to the local in, then the producer will be aware of the changes in. Okay, so with get in, this is what you get. But if you replace get in the loop here on line 2, if you change it to in, then you will get m plus 1 and 0. Okay? So make sure that you understand all of this and you think carefully about what's going on. Any questions on this? Okay, now another question. What's the range of possible values that may be returned by get in on line 3 and get out on line 4 of the consumer? So on the consumer, I have get in and get out. What are the possible values that can be returned here? So this is the consumer in the very beginning, before the consumer starts consuming anything. What will the value of in here be?
Depends on where the global pointer.
Okay, it depends on where the producer is. So what's the range? So the question is asking you to give a range.
0 to m minus 1.
0 to?
Both sides.
Yeah, 0 to buffer size minus 1. So the range is going to be, for in, it's going to be 0 to m minus 1. Why? Now there is an important concept here. So this is the concept of parallel programming. So even though this question it's asking you about the value of a variable, but the underlying concept here is the concept of parallel programming. The concept here is that we are at this point in the consumer, but there is a producer that is running in parallel, and we don't know where that producer is. So we don't know where in this range the producer is, but we know that it will definitely not exceed m minus 1. Why? Why do we know that it will not exceed m minus 1? When it gets to m minus 1, it's going to stop. Why? Because then the buffer will be full, and the consumer hasn't consumed anything yet. So without the consumer consuming anything, the producer will stop at m minus 1 at most. So the producer can be anywhere between 0 and m minus 1, but it will not go past m minus 1 because it will stop when the buffer is full. And the only way the buffer becomes empty is when the consumer consumes something. And the consumer at this point hasn't consumed anything yet. Okay? So this is the concept. Now get out. Out, what are the possible values for out at this point?
0.
Only 0. Because the producer cannot. If there is a single producer and single consumer, so the producer cannot change out. Okay. Now, the problem-solving question. Okay, so I'm not going to read it, I'm going to explain it. So you're supposed to have read this at home and attempted to construct a solution. So this is the problem-solving question. So here the point is to test your ability to read this question, understand it, and construct a solution. Okay. So now, let me explain it. What if there are multiple consumers? So we no longer have one consumer. We have multiple consumers. So if we have 100 items, we want each item to be consumed by one consumer. But we don't know how this will be divided. So it depends on how the parallel, it depends on the parallel speed, the relative speed of the parallel processes. So maybe, consumer 1 will consume 20 items. Consumer 2 may consume, say, 50 items, and consumer 3 may consume 30 items. We don't know. Now the point is, we have this code on the consumer side. Think about this. So this code will be executed in parallel by multiple consumers. Multiple consumers will be executing this in parallel. So when you look at this, with this description, which line here should go away, will no longer be valid?
Follow. The for I equal to line 5. Yeah.
So this line here, line number 5, is saying that each item is going to consume the item count. No, this is no longer true. It's no longer true that each item is going to consume 100. So the 100 are going to get divided on these different consumers. Now, how do you think that the consumers should synchronize? Then we will need something to tell a consumer to consume as long as there are items to consume. As long as there are some items that haven't been consumed yet, a consumer can consume. So now, what should we replace this loop with? So this loop terminates when this consumer consumes all items. But when there are multiple consumers sharing the same items, what should we logically replace this with?
Multi item.
Yeah, exactly. So we should replace it with a check on the number of items consumed. How many items have been consumed so far? If that's equal to the total number of items, then this consumer should exit. Or, in fact, every consumer should exit when the number of consumed items is equal to the total number of items. So one thing that we need to do is to replace this with a statement, an if statement that checks on whether there are items to consume or not. So then this means that we should put the consumer in an infinite loop that will break when the number of consumed items is equal to the total number of items. Now, where will this number of consumed items come from? Yeah.
From the consumers? Each individual one?
Yeah, but how? How? Yeah. So where should we put that count?
Random count share memory.
Yeah, we put it in shared memory. That's logically. So this should be in shared memory. We should add another number that tracks the number of consumed items. So let's call it consumed item count. So the solution is we add a consumed item count to the shared memory buffer. Now what should each consumer will check on this if it's equal to total item count or not. If it's equal to total item count, it's going to exit. Now what else should the consumer do to this consumed item count?
Protect it so that
Okay, yeah, protection is important. So we need to protect it because it's shared.
Increment.
And increment. So it should increment this. Each consumer, whenever it consumes an item, it should increment this consumed item count. But we have to be careful now. We should protect this shared variable with a semaphore or a lock. But now looking at this code, there are other variables that we must protect with semaphores and locks. Now with multiple consumers, what else becomes a shared variable that we must protect with a semaphore or a lock? Out. Yeah, with multiple consumers, out becomes a shared variable that may be modified by multiple processes. So basically, this should be in the critical section. And also this should be in the critical section. And in fact, if you think about this, all of this should be in a critical section. Remember, when it comes to critical sections, we try to minimize the size of the critical section, but we must, for correctness, we must put inside the critical section anything that is shared, anything that must be protected. So all of this should go in the critical section, plus the update of the consumed item count. This will also go in the critical section. So what remains to be outside the critical section is the processing of the consumed item. So the question is talking about processing of a consumed item. That's something that we put outside the critical section. So the code will be changed, will look like this. So we have an infinite loop that breaks or exits if the consumed item count is equal to the item count. Now, before we exit, we should remember to post the semaphore because we're waiting on a semaphore here. Okay? And so everything will go in the critical section except for the actual processing of the item. Now, if we put process item inside the critical section, will this be, from correctness point of view, will it be correct or incorrect?
Correct.
Yeah, from correctness point of view, it will be correct. But from efficiency point of view, it will be a terrible thing to do. Because then we will no longer have any parallelism. Right? If you put everything in the critical section, then you will have no parallelism. There will be no point. So remember that whatever is in the critical section is something that is executed sequentially. That you are not allowing multiple consumers to be doing at the same time. And if you put everything in the critical section, then there will be no point in doing multiple consumers and in doing all of this parallel work. So from efficiency point of view, processing an item will be done in outside the critical section. Inside the critical section, we protect access to shared variables. The shared variables here are out and the consumed item count, which we set here. Okay? Any questions? Yeah. So it's so this kind of question, it's challenging to solve a problem like this in the test. But in every section, there are some students, at least one student who can do this. In every section that I have taught, there is always at least one student who can do this in the test. Remember, it's a 50-minute test, so you get like 10 or 15 minutes for this. So in 10 minutes, you need to comprehend the question and to construct a solution. And there are always students who can do this. Okay, so now question number 3 is on process synchronization. Now in your test, there will be a similar question, process synchronization, and it will be on one of the synchronization solutions that we have studied thoroughly in class. So anything that we have done in class will possibly be in the midterm. It could be this, it could be something else. And this particular synchronization solution is a solution that we spent 20, at least 15 minutes. At least, I think it was like 20 minutes that we spent on this. And this is something that was explained thoroughly. which is what we did with all synchronization solutions. You know, the readers, writers problem, we spent like a whole lecture on that. Bounded buffer problem, we spent 2/3 of a lecture or something. And the dining philosophers, so we spent a whole lecture on dining philosophers. So any one of these will possibly be in the midterm. So make sure that you understand each and every one of these solutions very thoroughly. Because the questions that I will ask you on them are not going to be superficial questions. Oh, so question number 1. So this is the solution to the critical section problem that uses the test and set hardware instruction. But this is the long version. And why is this version long, by the way, for those who remember? Why is this long? So in fact, the first question is, lines 6 through 12. What are these doing and why do we need them? What's the problem that they're trying to solve, or that we are trying to solve with lines 6 through 12? So it's a problem that was in the solution prior to this. So we studied a solution, a simple solution prior to this that had a problem, and these lines are trying to solve this problem. What's the problem? So it looks like no one has started reviewing the material yet. It's a starvation problem. So these lines are trying to solve the starvation problem. How? What's the concept, at least, away from the code? Conceptually, how are we trying to solve the starvation problem here? By having the process that leaves the critical section check on the processes that are waiting for the critical section and giving the critical section to one of them if there is one waiting. So, again, this is something that we did not go through quickly. It's something that we discussed thoroughly in class. Okay, so the problem is starvation, because with the previous solution, it was possible for one process to keep taking the critical section while other processes are waiting. The above code has two Boolean variables, lock and waiting. What are the initial values? So what should the lock be initialized to? So is the lock initially locked or unlocked? Unlocked, yeah, so it should be false. And waiting for each process, should the process be initially waiting or not? No, so it should be false. Both of them should be false. Okay, because so if both are, so waiting, if waiting is true and key is true, we wait. Otherwise, if one of them is false, we don't wait. Okay, what's the case that is handled by lines 9 and 10? Or in other words, what does the condition I equals J mean?
No process is waiting.
Yeah, exactly. So I equals J means that no other process is waiting. Okay. Now, suppose that we have 10 processes, 0 through 9, and process 6 is currently in the critical section. 6 is in the critical section. Processes 2, 5, 8, and 9 are waiting. 2, 5, 8, and 9 are waiting. And this is in. Now the question is, when process number 6 is done, which process will get the critical section? 8. Yeah, process number 8. Because it's going to do the checking in this direction. So it will check on 8, then it will check on 9, then it will check on 2, then it will check on 5. So it will check on them in this order. Okay, if you understand the solution. if we use, okay, so this is an interesting question. If we use a mutex semaphore instead of the test and set instruction, what will determine which of the waiting processes will enter the critical section after the current process is done with it? So if we use a semaphore instead of using this solution, instead of using test and set, if there is a critical section protected by a semaphore, what will determine which process will get the critical section next with semaphores? On semaphores, we use, so instead of using this, yeah, go ahead.
Whichever process requested it first.
Whichever, yes, assuming that the queue is the first in, first out queue.
Oh, yeah.
So the more precise answer is whichever process is at the head of the queue. But usually it's a first in, first out queue. So if it's a first in, first out queue, the process at the head of the queue will be the process that has been waiting the longest. Okay? So basically the point here, the answer is, with semaphores there is a queue. There is a queue, and processes will be in a queue, and the process that happens to be at the head of the queue will get the semaphore. Now, compare it with this. So here, this solution here doesn't take into account how long a process has been waiting. So maybe it's going to give it to 8, and maybe 8 was the last process to request the critical section. Maybe 5 has been waiting for a long time. But with this scheme, it's going to give the critical section to 8. But the semaphore does not do this. The semaphore, with the semaphores, the critical section will be given to the process that is at the head of the queue. Okay. So now, so this is a sample question. So what this means to you is that in order to prepare for the midterm, you must study all the synchronization problems that we have studied in class and all the different solutions, and you should be able to answer questions like this on them. And sometimes you should be able to modify the solution in a certain way. Okay, so you need deep understanding of these solutions, not just a superficial read. Okay, so now let's go through the conceptual questions. So there are multiple choice questions, and there's a free response question. And I think this question was asked in the quiz one for this section. It was in this section, right? Mm-hmm. Yeah. So we have answered this. If the time quantum, long-time quantum means bad responsiveness, and short-time quantum means wasting too much time in context switching. Now, multiple choice questions. Now, with multiple choice questions, make sure that you read all options, all alternatives, because because there are sometimes the answer is a combination of answers. So sometimes both C and D are correct. So don't just circle the first option that looks right. Make sure that you read all of them, and you read them carefully. Okay. Okay. What are the advantages of dividing an application into multiple threads relative to dividing it into multiple processes? Okay. So, utilizing a multi-core system, is this an advantage of threads over processes?
No.
No, it's not. So it's a good thing that you can achieve with both equally well. So you can utilize a multi-core system using threads by dividing your application into threads, and you can also utilize a multi-core system using processes. by dividing your application into multiple processes. So when we say advantage of X relative to Y, we're looking for something that is good in X, but not good in Y. Or at least is not as good in Y. But if it's good in both, then it's not an advantage of X relative to Y. So this is not an advantage. B, one slow task, one slow the whole application. Again, this is something that you can achieve with threads and processes. So A and B are not advantages of threads relative to processes. They are good things that you can achieve with either multiprocessing or multi-threading. Using less resources, yes. So when you divide your application into threads, you use less resources than if you divide it into processes because
Threads share the same.
of resource sharing among threads within the same process. So one important concept in threading is that threads within the same process share resources. Easier communication using global variables. Yes, so this is an advantage of threads. And in fact, we have seen this in the assignments. In assignment number 1, we did multiprocessing. In assignment number 2, we did multi-threading. So when we did multiprocessing in assignment number 1, there were no global variables that we could use. So we used shared memory to do inter-process communication. In assignment number 1, we had to use shared memory. In assignment number 2, we didn't need shared memory because we just used global variables to have the different threads within the same process communicate. So this is something that we have experienced in the programming assignments that we've had. So the answer is C and D, which is F. Okay, so that's why you must read all of them. In a given program, only 1/6 of the code is parallelizable. What's the maximum speed-up factor that can be achieved on a dual-core system under ideal conditions? So, by the way, here you don't have to memorize formulas or anything. By the way, you can have a cheat sheet in the midterm. So you can have one cheat sheet, and you can write on both sides, and you can use any font. So students ask, can I type? Yes, you can type, and you can use any font size. So if you can use .000 if you want. You can put the whole book on a cheat sheet if you want, but then you need a way of reading that, a method for reading. So yeah, so you can have a cheat sheet and you can write formulas. But here for this question, it's it's very intuitive. You don't have to memorize formulas. It's saying that 1/6 of the code is parallelizable, so you can parallelize a sixth, while the 5/6 are not parallelizable. So it's 5/6 is the part that you cannot parallelize, while the 1/6 is the one that you can parallelize, and you can divide it by dual. So dual core, it means you have 2 CPUs. So this is the one that you can divide by 2. And so the idea is 1.0. If you don't parallelize anything, then that's 1. If you parallelize, this is the sequential. You cannot parallelize it. This is the parallelizable. So this is very intuitive, and it's you don't need to memorize formulas or even you look at the formula that you have on your cheat sheet. So in this case, it's just 5/6, which is 10/12 plus 1/12, and the answer is 12/11. Yeah, so this is a question that many students got wrong for some reason. So it's, just be more intuitive. I think it's, I guess some students just look at the formula and somehow they get confused and they don't know which one is the P and which one is the S. It's intuitive. This is the one that we can parallelize, so this is the one that will get divided by the number of processors. Okay. How does protecting a critical section with a semaphore ensure mutual exclusion? This is an important question because it's about understanding how semaphores work. So let's read the alternatives. When a process is in its critical section, no other process is allowed to be in a critical section. Is this true or false? It's false. Because if a process is doing wait on X, and it's in the critical section, and I think I did this when I explained semaphores. I did this, wait on X, and another process is doing wait on X, post X, and the third process is doing wait on Y. Critical section, post Y. So, the operating system is guaranteeing you that if a process is here, this process will get blocked here because it's trying to access X, semaphore X. And this will be in the queue, in the waiting queue for semaphore X. But there's no reason to block this. So this is just waiting on Y, and there's no reason to block this. It's just a different critical section doing something totally different. Okay? So this may be in its critical section. Okay? So number one is false, because other processes may be in different critical sections. When a process is in its critical section, all other processes are placed in the waiting state. Is this true or false?
False.
Yeah, it's definitely false. It's just ridiculous. You cannot just, because one process is in its critical section, you cannot just suspend all processes in the system. That's what it's saying. If one process is in its critical section, then suspend all processes in the system. Doesn't make any sense. When a process is in its critical section, any process that tries to access a critical section that is protected by the same semaphore is placed in the waiting state. So this is the right answer. So that's why you must read all alternatives carefully and think about it. When a process is in its critical section, it never loses the CPU until it completes the critical section. So again, yeah, this is false. So the operating system is not saying that if you are executing this critical section, I'm going to give you the CPU until you are done, because what you have in here can be fairly lengthy. Your critical section could be very, very long. And a process could even request I/O in a critical section. When you are in a critical section, there's nothing that prevents a process from requesting I/O. Then it will lose the CPU. So it's not about losing the CPU, it's about not allowing other processes from accessing a critical section protected by the same semaphore. Okay. Now, both, of course, all of these options are not right. So these options are there to maximize the number of alternatives, which minimizes, minimizes the chance of getting something right by guessing. So that's the purpose of to reduce the chances of a guesser. To have all of these options. So that's why, I try to have 7, 8 options. If I could have 100, this would have made less, more rigorous. With 100 options. Yeah, so I don't want you to guess, I want you to think. That's the point. Which of the following is not true about shared memory and message passing. Okay, so when the question asks not true, what I recommend is that you go through all alternatives and mark each one as true or false, then select the one that is not true. It's just because many students, I think, get this wrong because they just mark something that is true. It's saying which one is not true, which option is not true. So basically, don't circle until you have gone through all of them and determine whether it's true or false for each one of them, and then select the one, circle the one that you think is not true. Okay, so here, shared memory is slower than message passing on all multiprocessor systems. Is this true or false? False. We never said that it's slower than message passing on all multiprocessor systems. We said that sometimes on some multiprocessor systems, shared memory may be slower than message passing. And what's the cause? What's the cause of the slowness of shared memory on multiprocessor systems? What was the cause of the slowness?
I think that's the shared memory.
No. Cache coherency. So this is the hardware concept. Yeah, so it's cache coherency is the cause of the slowness of shared memory on multiprocessor systems, but it's not necessarily slower on all multiprocessor systems. In fact, the chances of being slower go up when you have more CPUs. So this happens when you have many CPUs. How many, we don't know. So that's why making the statement that it's slower on all multiprocessor systems is not a true statement. Shared memory is faster than message passing on all single processor systems. Yes, so based on what we have studied the cause of the slowness is cache coherency. Given what we have studied, shared memory is faster if there is a single processor, so we don't have the cache coherency problem. On a single processor system, we don't have the cache coherency problem, so it's true. In shared memory, kernel intervention is needed only to set up the shared memory block. Yeah, that's true. In message passing, every send and receive goes through the kernel. Yeah, that's true. So everything is true except A. So in this case, the right answer is A because it's asking about something that is not true. Okay.
I think you skipped problem 4.
Yeah.
I can't believe I did this again. I skipped problem 4 with the other section. I don't know. I hate problem 4. I don't know why. I can't believe I did it twice. Well, because I think it's because it's about semaphores, so I thought it's the same as problem 3 or something. Yeah. So if I was in a test, I would have lost the points for this. Which of the following is true about spin locks and mutex locks? In fact, it's a very interesting question, and it's a concept that we discussed thoroughly in class. The difference between a spin lock and a mutex lock. Okay, so which of the following is true? A process waiting on a spin lock uses CPU cycles, but a process waiting on a mutex lock does not. True or false? Yeah, this is true. That's the whole point, in fact. A spin lock is you're spinning, busy waiting, and on a mutex lock, you are in the waiting queue. Using mutex locks may involve more context switching. Well, it's true. It's true because it's definitely if you are spinning and the lock becomes available while you have the CPU, you will get the lock without any context switching. If one process is spinning and the lock becomes available in a short period of time, the spinning process may get the lock without losing the CPU and without any context switching. Why? If you do a mutex lock, whenever you wait on a lock, you are in the waiting state. So you lose the CPU, and a process loses the CPU, this means that there is context switching. So in order for this process to get the CPU again, it will have to go through the ready state. When the lock becomes available, to go through the ready state, then it's in the ready queue, then it's competing for the CPU, and then it will get the CPU, but when it gets the CPU, there will be context switching. Okay, so let's think about 6. Using spin locks is more efficient on a single CPU system.
False.
So this is false because on a single CPU system, you are on a single CPU system, you are taking CPU cycles from the process that is in the critical section. Using spin locks is more efficient when the process waits for a long time. True or false? Yeah, it's definitely false. So with a spin lock, spin lock is good when the waiting time is short. If a process is waiting for a long time, then it's wasting lots of CPU cycles. More time is more waste of CPU cycles.